So welcome to today's webinar. This is part of the Blasting and Pit Slope Performance course, and today's topic is blast timing optimization for mitigating slope damage. This is a Ask the Experts live webinar, so we've got our panel of experts who I will introduce in just a moment, but first I'm going to give you a little bit of background on the Geotechnical Center of Excellence we're putting on this webinar for you today. So the GCE, as it's often known, we're an industry-funded and member-led group at the University of Arizona. We're part of the School of Mining, Engineering, and Mineral Resources, and we pride ourselves on bridging gaps between and within academia, industry, and fields of study. And we also do collaborative research and provide professional development education opportunities, such as the webinar that you're tuned into today. As I mentioned, the GCE is member-funded, member-led, so here is a list of our member companies. You can see it's a who's who of the industry. If you would like to become a member or at least start that conversation, we'd love to have you. You can find us on LinkedIn. You can go to, oh gosh, I can't remember the exact website address, but maybe one of my colleagues can put it in the chat for you. But just get in touch with us. We'd love to start that conversation with you. So this webinar is based on our Blasting and Pit Slope Performance Professional Development course. It is live currently. This is an online course. It is presented by industry experts, and it, like I said, it's ongoing right now. The content is open for many more months. You can still register today, and you can scan the QR code there if you'd like to learn more. And I think one of my colleagues will also put the link to that registration in the chat for me. I want to give a huge shout out to our lead technical advisors, some of which are here joining us today. There's Pat Jenks, he's a manager of geotechnical engineering at Nevada Gold Mines. Phil Morris, he's a mining engineering consultant. And John Silva Castro, he's with Dino Consult. Without them, this course would not be possible. They provided a lot of their time and expertise to developing this course. This course was also underwritten by the Large Open Pit Project, so a huge shout out to the LOP for their support. Just a little bit of housekeeping. If you're joining today, you are muted and your video is off, so don't worry about any of that. But we encourage you to ask questions. You can do that by using the Q&A function in Zoom. It's different than the chat function, so we encourage you to use the Q&A. That kind of helps us find the questions. You can ask anonymously if you'd like. You can also vote, give a thumbs up to other people's questions if you'd like that question answered. This is a recorded webinar as well. We'll post this on the course D2L site. We will also post this to the GCE's YouTube page, and I think one of my colleagues could be so kind as to put that link in the chat as well. Just a quick disclaimer to note that the views and opinions expressed by our panelists are their own, do not necessarily reflect those of the GCE or any affiliated organizations. All the webinar content is intended for educational purposes only. It is not intended to be substitute for site-specific professional advice or analysis. So thank you for bearing with me on that. So just a couple of introductions, starting with the Geotechnical Center of Excellence webinar team. I will be the moderator for today's webinar. My name is James McNabb, Senior Research and Development Engineer here at the GCE. I'm joined by two of my colleagues, Jillian Noonan. She is also a Senior Research and Development Engineer. Good morning, Jill.
Hi, everyone. I'm really looking forward to an interesting session today. Thank you so much for all of our amazing panelists for being here. And yeah.
All right. And also Cheryl Bulkowski. She's our Professional Development Program Lead. Hello, Cheryl.
Hello. Good morning, everyone. We're glad you're here.
All right. Now we'll introduce our expert panel, starting with John Silva Castro. He's the Director of Dino Consult, Value Capture Global, and he is also a lead technical advisor for this course. Hello, John.
Hi, good morning. Thank you, everybody, for joining today.
All right, next we have Pat Jenks. He's the Manager of Geotechnical Engineering with Nevada Gold Mines, and he is also a lead technical advisor for the course. Hello, Pat.
James, welcome everyone. Greetings from Elko, Nevada. Thank you for joining.
All right, next we have Thierry Bernard. He is a General Manager of DNA Blast Group, and he is a course contributor. Hello, Thierry.
Hello, everyone.
Thank you for joining and happy to be with you.
And he is joining us all the way from France, so appreciate you tuning in late in the evening. All right. Next, we have Paul Schmiesing. He's a drill and blast subject matter expert with Nevada Gold Mines, and he's joining us as one of the industry experts. Hello, Paul.
Hello, everybody. Thanks for joining.
And we have Chris Dahl. He's a technical manager with Southwest Energy, and he is a contributor to the course. Hello, Chris.
Hello, James and everyone. Welcome to this session. Looking forward to a productive what is us late morning for us. I am calling in from Tucson, Arizona as well.
Beautiful Tucson, 60 degrees.
Severe clear.
All right. So now we'll get into some kickoff questions, and we'll start off a question for John. Okay, so what are some of the key assumptions you make when designing blast timing and sequencing, and which of those, if wrong, have the biggest impact on blast outcomes? John, if you'd like to kick us off.
Yeah, first, the timing design maybe needs to set what do you want to answer. Do you want to control vibrations? Do you want to improve some fragmentation? Still, we have not found the secret formula to bring together both things like fragmentation and vibrations. So you need to sometimes you need to sacrifice one over the other depending on what do you want, the angle. However, assuming that your timing is set, definitely the sequencing needs to play a role. And usually the main objective of the sequencing is like everybody says, shooting to the free phase. So you have to take advantage of the free phase of the free areas of the shot, and that will control things like fly rog or even increase on the vibrations in some cases. Sequencing also controls sometimes you design your pattern, burden spacing, control these variables, but you can even change in the sequencing the actual burden, the actual spacing. And I don't have here the graphics to show that, but say if you have a rectangular or a square pattern, and you shoot your rows and holes one by one, the burden and the spacing is what you design. But if you use an echelon or you modify with an angle, your burden will change. So as I always say, blasting is an art. So it's kind of a trial and error, of course, with highly equations and education. You start to learn how your deposit, your areas will behave. What can we go wrong? A lot of things, from fly rog, air overpressure. So yeah, this is what I will say basically.
Great. Thank you, John, for kicking us off there. If anybody else would like to chime in on this one, feel free to.
I'd like to just reiterate one of the things that John said about the burden spacing and how that ties to the sequence. I mean, you got to think about how that shot is confined. If you're running a square pattern or square hole layout, you can have some flexibility, for example. But if you have a rectangular hole layout, you're depending on how that pattern is or the firing sequence is set up, you may end up having a greater confinement in one direction versus another if you choose to change that sequence of firing. So it's just something to keep in mind.
Yeah. Thank you, Pat. All right. That's it. We'll move on to the next one. Thank you, John, for kicking us off. This next one is for Pat. The question is, Several practitioners in this course have emphasized that proper implementation of the blast design, such as achieving design drill depths, loading, stemming, etc., is critical to success. When you see poor blast results, what clues lead you to suspect that timing or sequence is the primary issue rather than design, implementation, or geology?
Well, I guess one of the first questions I'm going to ask, going back to what John said, the phrase he used, free face. Did we shoot to a free face? Is that shot confined or over confined in some way that the energy is going to go, more energy is going to go into ground vibrations and cause damage to the wall? So that's one of the first things I'm going to look at. And it is some of the key, say, performance monitoring tools that I look at. I love looking at the videos and watch that blast perform. Is there evidence of backbreak at the crest that is going to influence the long-term performance of that crest and crest loss? Are there evidence of geologic structures that maybe weren't previously mapped showing up within that shot muck, and understanding how that influenced the performance of the shot? Are there significant energy troughs at the margin of the pattern, the sides, the end, etc.? Is there debris coming off the high walls? Those are things we're going to be looking for. Also within that video, you might be able to pick up undetonated holes that will help give you some clues to performance. Looking at the slope performance data itself, things like radars, critical for understanding how that blast influences the performance of the wall. Is there evidence of blast-induced deformation in the radar or prisms? This could manifest itself as an increase in the magnitude of displacement and velocity temporarily correlated with shot time. So all key things that we want to be looking at. Other data, seismograph results and the targets. Are we meeting the targets? Are we exceeding what those target values are with respect to PPV or frequency? And then, ultimately, post-blast inspections after you muck out that shot, particularly as you're getting the final wall. Do we see features in that wall that suggest that, it was over confined, but a lot of backbreak, and the energy, instead of going parallel to the wall, is going into the wall? For certain ring-shaped features, we're getting suggesting adverse backbreak that's going to result in crest loss. Those are some of the things I look for.
Great. Thank you, Pat. If anybody else would like to chime in on this one, feel free to.
I'll echo Pat's input there. Agreed wholeheartedly, especially on the last video. Videos are worth their weight in gold and many times offer you a very, very quick opportunity to identify the root cause of what may be the issue/failure as it relates to this subject.
Yeah, great. Thank you, Chris. All right. Thank you all. That's it. We'll move on to the next one. This one is for Thierry. So the question is, given the number of variables in blast design, such as powder factor, burden, spacing, geology, and so on, how do you go about determining an optimized blast timing and sequence solution? Thierry?
Yeah. When we're looking at the blast timing and the best delay to optimize the blast, I will say that the first thing is, as it was mentioned initially, is to define first the objectives. Are we looking to reduce the PPV or shift the frequency, or looking for a good fragmentation or a good movement or heave, or to control dilution? But let's say when you have decide which objective is the key one, or you have prioritized your objectives, then the sequence itself, the order of detonation, as we said, shooting through the free face is the first one. If the blast has a free face, because some blasts they do not have a free face, but when you have one, that's the first one. Then the timing, if we're looking, for example, for vibration, there's two key parameters. The first one is to be sure you don't have any overlap in between charges. So as to be sure you have individual time per hole, not shooting multi-hole at the same time. So if you shoot with electronic, it's very easy to do that. If you shoot with non-electric, it's more difficult, first because of the inaccuracy of the system and the limited, let's say, configuration of timing that you can have. But when you have ensure that you don't have any overlap, or you have, let's say, one charge associated to one initiation time, the second thing is to look at the timing that can create destructive interferences in between the holes if your goal is to minimize vibration. And for that, you can use what we call signature hole processing or seed waveform processing. It's basically using the trace or the waveform of a single hole or a single charge, and use a computer to find what is the best delay to create destructive interference in between the different waves. This works well when you are in far field. So it means you're quite far from the blast. If you are in near field, it's more complicated, and you need some advanced computations and measurement on the field to get this works. But in far field, it works very well. You can use the same principle, for example, if you try to optimize fragmentation, but it's going to be the other way around. You're not trying to create destructive interference, for example, at the house location. You're going to create constructive interference in the block itself. So you will add the waves together in the center of the block to do more, to apply more constraints or more strain on the rock and create more fragmentation. And these two are totally different, because if you create constructive interference, even if it's in the block, you will increase the vibration. So it's hard to combine, for example, reducing the vibration and increasing the fragmentation. That's the main parameters that you can work on the timing to optimize the sequence.
Very good. Thank you, Thierry. Would anyone else like to chime in on this one? If not, we can move on to the next. All right, going once, going twice. All right, thank you, Thierry, for that. Let's see, this next one is for Paul. Question is, what specific conditions, whether geologic factors or desired blast outcomes, would prompt you to take a much closer look at the timing and sequencing of a blast design before it's implemented?
So I guess a lot of the other questions are related to kind of how I would answer this too. To me, it's kind of that whole complete picture. But specifically when the geology, you're going to look at the, do I have a bunch of faults coming in close, into the wall, that if I do open up a shot, is the energy going into those faults and going to open them up? So a way to fix that would be then to change the direction of the blast. So sometimes, like recently, we had to do that when the free face was the direction we want to shoot, but it would have sent the energy right into these fault structures. So we had to change the direction. And then so by doing that, now we don't have a free face. So at the beginning of the shot, you have to do kind of a pill shot first to get to create a new free face that then we would direct what we've been trying to do is direct the recoil as parallel to the wall as possible, and instead of trying to reduce the amount of impact into the wall too. The other big thing that we've been doing is when assessing how are our blasts doing, we're using seismographs And one of the things that we can pick up from that is, hey, the timing was working really good through the first third of the shot. Next third of the shot, okay, the vibration's really high. Next third, it's back down to normal. And so when we kind of look at it, gives us, okay, what's going on that's causing in the middle? And then it's, oh, there's a dike on this end, or at the beginning third, and then there's a fault on the other third. So now we know in this middle section, it was being controlled by a dike and a fault. Sure enough, the ground's really sheared up in that zone. So the timing we're using in that section wasn't right. So then we'll try to create a signature hole for that domain. So to me, it's what I'm finding is we through that analysis pick up on the different domains that we're dealing with, that generally one timing for the whole bench isn't the same timing we should be using. Some of the other things is the corners and going around corners. We may one side of the wall is really reactive, the other corner isn't. So then that'll help us control which, knowing that, then maybe we do a shot break instead of trying to shoot both shots at the same time in that corner. To create a free face, then to help out. So when we do shoot in that corner, that we've done what we can to try to help us out and minimize the more sensitive ground area. So corners, let's see. I think I kind of mentioned about how we're trying to shoot more parallel when possible. And then the other thing we've seen is definitely paying attention to the amount of holes going off per delay in these sensitive areas. With the electronics, it helps. We can do the signature hole, but what we're also finding is if we have a bunch of holes, since they're electronics, they're all going off at exactly the same time. We can see that it impacts if we if we have two holes going off at the same time, we can see it's double the amplitude. So then we'll try to adjust the timing. So instead of opening it in the middle, if it's a production shot, maybe if we shift it to one side, that'll create a timing pattern that reduces the amount of holes per delay. And we've seen that work well for us in these more challenging geological conditions. So let's see, corners. The other thing that'll happen too in these corners is usually the outside row, which is the row closest to the wall. A lot of times there's extra holes in there because you're going around a gradual corner. And you need to slow the inside timing down so that way your angle initiation isn't rotating and impacting your ground or your corner hard. So I got corners, shot, recoil, shot direction, and faults. I think I've kind of hit some of the main things. I mean, I'm getting asked these questions about 3 times a week.
It shows.
Yeah.
That was a very thorough answer. Appreciate that, Paul. Great. Excellent. Would anybody else like to jump in on that one?
Well, I'd just like to add that, this question, I think, highlights the importance of having good performance data, good seismographic data so that you can address some of those questions that Paul raised. Understanding where those blast timing domains fall with respect to the geology, I think are going to be critical to you, and that's why it's important to have that good sound seismograph data, good signature hole data from which to base good timing. And at the end of the day, you may not shoot through all of those different zones. You may end up setting up stop lines where you know that you're going to have 2 different or 3 different timings, as Paul alluded to, and you'll set up a stop line with one set of timing and then have another shot with a different set of timing in order to minimize those ground vibrations and maximize your pit slope performance and minimize the potential wall damage.
Yeah, great. All right. Very good. Well, thank you both for that. Let's move on to our last question for the panelists. This one is for Chris. All right. So as a contractor, you may be responsible for implementing the blast, but not always in control of key parameters like timing and sequence. How do you manage that situation and still protect the slope?
Yeah, so perfectly appropriate question for my role as a contractor, obviously, and I try the best I can, and we as a company to keep open lines of communication with the end user to understand what the goal of the blast is, as has been outlined here from the prior topics. Understanding the goal of the blast, be it fragmentation, vibration control, amplitude control. Pick the topic, and just make sure that we're communicating, controlling what we can control, and then helping to make sure that the ultimate goal of the blast is understood, and providing some input and help to achieve that goal, be it via the signature holes or any of the tools that we have to bring to bear for the subject. So yeah, good communication from a high level is my blanket answer for that.
Yeah, very good. Challenging position, I'm sure. All right. If anybody would like to chime in on this one, I know some of you are contractors as well. If not, we can move on to other questions.
As an owner's representative, I would echo Chris's comment about communication. I mean, it's key that all the key stakeholders are communicating openly and transparently about, what the objectives of the project are. Don't just rely on that contract to provide a shot service. Tell them what your goals are and what your expectations are, so you can work through it together. And if there are issues that develop, that you can solve them through the communication process.
Yeah, that's an important addition. Thank you, Pat. All right. Well, we've got some live questions now from the audience that we'll go to. I see a couple of them have come in. Really good questions. I encourage you, if you're tuned in today, to type in your questions. This is an amazing opportunity to ask your questions to panelists of experts. So let's start out with our first one here. This is from Elena, and we have paraphrased your question, Elena. But it's a very good one. So what considerations should be applied in weak alluvial overburden? And we were chatting about this a little bit before the webinar started. So maybe Pat, if you want to take this one on first, I'd appreciate that.
Sure. I think this is a situation that's come up at a couple of our operations over the last several years, and a lot of it boils down to is that weak alluvial overburden is cemented or not. And Chris will reflect on this at Crossroads when we're bringing down some of the waste and overburden material over the ore body. One of the things that we did is we did a lot of free digging within these alluvial materials, both with hydraulic and electric rope shovels. And I think that's a key thing to have a conversation with your operations team. Are the shovels capable of free digging in that material before you start shooting it? Because one of the negative outcomes of shooting in that alluvial material is that you can create blast-induced voids that then become a different type of hazard. So those are some things to consider. As you maybe transition from a non-cemented material to a cemented one, having good, sound geologic and geotechnical exploration to identify where those cemented zones are located in the subsurface will help you better transition from where you might be able to free dig to where you might need to shoot that cemented material in order to load it with your loading equipment. So those are some of the things I would suggest that people consider.
All right, thank you, Pat. John, I see you've unmuted.
Yeah, one thing is related and not related with the specifically this weak alluvial material, right? Sometimes you have to think, okay, the first question what Pat's or the thing Pat was saying is, do I need explosives? Right? This is the first question. Say, sometimes you also need to see how fractured is your rock mass. Do you have explosives to actually create fractures and fragmentation, or you just need to move the material? So those are the things you need to take into account also at the beginning, you know.
Yeah, great point. All right. Anybody else? This is a really good question. I'm sure. I mean, most operations deal with this.
Yes, James, I would like to add that if you have decided to blast, if you think you have to blast it, it could be useful to have a drill with measurement while drilling on board and use this information to know exactly the hardness of the rock, I would say the weakness of the rock, plus or minus, and to use the correct explosive depending of the hardness of the rock that you measure with the measurement while drilling. Because generally in such weak material, you've got a great large difference from hole to hole. It's the rock is harder on some area and softer on some area, and you should not use the same type of explosive. Maybe harmful on some part, emulsion on the other one, depending on the hardness. That help a lot in this kind of material.
Yeah, great. Thank you, Thierry. Chris, I saw that you had unmuted earlier. If you wanted to add anything.
Yeah, just quickly. Pat has seen it. Paul has seen it in Nevada. I mean, sometimes the answer is no explosives, right? We've seen success with just line drilling, no explosives, no timing. Good success in alluvium applications. Great for high wall mitigation, slope control. Just drilling a line of blast holes and being able to dig a 90-degree face to them in some of these alluvium situations.
Great. Thanks, Chris. Okay, very good. Thank you for the question, Elena. All right, we'll move on to the next one. This one is about software. What are the best applications of software tools you would recommend for tracking and anticipating blast-induced damage to high walls? I'm looking for a program that incorporates detailed rock mass parameters and accounts for jointing and rock strength. Most of the software I've found so far focuses primarily on explosive energy rather than the geological aspects. So I know a lot of you are quite heavy into the modeling aspect of it. John and Thierry in particular, if one of you would like to get us started on this one.
Okay, I can start. I don't know all the packages that exist on the market, but from our side, we developing the iBlast software, and when we're looking at protecting the high wall, the principle that is used is to work on the vibration level on the high wall, so calculating the critical PPV that you don't have to exceed on the high wall. And this is based on the rock mass parameters, basically all using the UCS, the UTS, the P-web velocity, and the density of the rock mass. So this is working well. And if you have a map of your rock mass with different parameters, then it can give you some different critical PPV, not to overpass in different area, and you can then design your timing based on that. As regard let's say the cracked or the joints, so far we are not handling that, except if you use a signature hole and you record the signature hole, let's say behind the crack and the joint, so the signature hole includes in the waveform the effect of the joints, but that's the only way that we manage the joint in our software.
Great, thank you, Thierry.
I will add to that is remember that all models are wrong, some are useful. So we are getting to the point that we can put reality on the computers. But for this particular point, I will suggest testing on the field. So there are some tests that you can blast particular holes, put sensors, collect the PPV or acceleration, and came up with. There are some theories where you can combine and estimate what is going to be the critical PPV for the slope based on the testing and some basic analysis. So I will suggest a combination between uh, analysis through a software, maybe yes, or through the equations, basic equations, PPV, Hollenberg and Pearson can be used. For example, there are a bunch of now numerical methods, finite elements, discrete elements. I mean, you can play with those, but always combined with testing on the field and calibrations for models.
Great.
Yes, fully agree with John. Even if you do modeling, and that's what we do, but the key things is to acquire a good field data that will characterize your rock mass. So, 100% agree that the modeling without any field data doesn't really make sense.
Yeah, good point. All right. Anybody else?
That's a good question for Jason Fertney.
It is indeed. Yeah. He was invited to be a panelist today, but unfortunately, I think he's out of country. So
Too bad. Yeah, I mean, I know the Itasca guys are working on some of this, but why? To Thierry and John's comments earlier, you got to be careful about garbage in and garbage out. Having good sound field observations, I think, are really, really important in blast performance and being successful as you bring down your wall.
got to look up from your computer every once in a while.
Yeah. Get out of the air conditioning.
All right, great. You know what? I've actually got a pretty good follow-up question, I think, here. Let's go to this one. Yeah, I think this is a good follow-up. Prior to and/or following adjustments made to optimize blasting, what methods are mines using to assess/quantify the degree of slope damage before and after blasting, and how to reasonably estimate how deep into the pit wall the damage zone extends? So, how are we assessing that performance?
Okay, I can start.
Yeah.
I will see two ways of doing that. The first one is to use cross-hole tomography. So you drill hole on the slope and you do tomography and you measure the P wave velocity in between the holes, and you see where the P waves is decreasing or where it's stopped decreasing, and you're reaching the full rock mass. You see the damage area and how deep is the damage area in the wall. This is working very well, but it's not an easy thing to implement, and it's really expensive. So it can be it's done in underground mines sometime, because that's the only way where we can when you can assess the damage, drilling the holes from the gallery perpendicular to the gallery and measuring these P waves with cross-hole tomography. For surface mine, it's very expensive and not easy. And one of the second way is to measure vibration. So to have sensors on the slope at different location. Sometimes you can put the sensor in the slope in a hole, and then you build either your regression regression analysis law with your K and alpha factor, and you can calculate how far you reach your critical PPV, so you know how deep is the damage in the rock mass in the wall.
Great. Thank you, Thierry. Anybody else? Pat?
Yeah, just I think on the second part of that question, there's the large open pit project has funded a couple of projects in that regard, and had some mixed results. Some promising where uh, core holes were drilled into the high wall uh, prior to mining or during the first phase of mining, and uh, the practitioner took a televiewer tool and measured discontinuities as a function of the depth, and then placed a PVC pipe or something in the hole to preserve it, so that the second phase of mining came. They stripped off that next phase, and then they measured the discontinuity frequency again, and that's one way. It's a bit on the research side of things, also not cheap, time consuming. But that's one way that people have been considering that, the second part of that question. And a bit of this ties back into D factor that I think is discussed a little later in the course in section 6 and 7. It's in my mind, a bit of an unanswered question. Where does blast damage end and relaxation of the pit wall begin? That could easily be confused with one another at least in the near field. So I think there's a lot of unanswered questions here on our part.
Yeah, very good.
Future research opportunities.
Yeah, our very own Jillian Noonan, who's assisting me in today's webinar, is actually doing her PhD on the D factor. So more to come there. All right. That's all we got on that question. Thank you for whoever posed that question. It's very good. All right, let's move on. This one is from Christian. A lot of specifics in here, but I think we can definitely generalize this one as well. So while the life of mine goes, we expand deeply and laterally, so we get to primary sulfides, where we have harder rocks like quartzites. Geology is an issue, and we have to choose explosives of low density, such as 1.1 to 1.2 grams per cubic centimeter, to look after the slopes. Velocity of detonation 2,000 to 3,200 meters per second for wall control products. But the mineral processing plant asks for target rocks between 1.5 to 2.5 inches. How could you manage this challenge? So obviously a lot of specifics there, but I think there's a generalized question there as well.
I'll speak to this as an owner's rep to some degree. This is where having good engagement with all the key stakeholders and understanding what those outcomes need to be, as Terry and John alluded to earlier in the webinar. Fragmentation may be the key in the production part, but in order to preserve wall control and pit slopes, we may need to transition to not hitting rock so hard that it fragments it to 1.5 or 2 inches. We may have to. There's got to be a give and take there, and that also influences the geotechnical slope design. For example, if we are damaging that rock mass near field to the high wall, we're going to likely have flatter inner ramp slope angles, and our waste stripping ratios are going to be higher than if we took a bit more care with that wall. So there's a lot of things to think or to consider in here, and it needs to be a really broad conversation between a number of the stakeholders at that site.
Yeah, and the other point to complement what Pat is saying is why we have these different, let's go to say, techniques to wall protection. So we have trim shots, pre-split, buffer holes. So you can sacrifice some area close to the slope. Let's go to say sacrifice in terms of fragmentation, but you can produce the product you are looking for maybe at some distance away from the slope. So this is what Pat says is when the processing plant knows that we are shooting close to the wall, the fragmentation is not going to be that ideal that they are looking for, you know?
I will add that this challenge is to a certain extent certainly manageable if you consider that the fragmentation is linked to the powder factor and the damage to the slope is linked to the charge per delay. But generally, because the mines, they use a large hole, we have a significant charge per delay, and we don't know how to deal with that. Just because for production you need big holes and big pattern. But if we could have a small pattern, so maintain the same powder factor to create this 1.5 or 2.5 inches rock, the charge per delay will be very small and the damage to the slope will be lower. But this is not compatible with high production, or it will cost a lot because it means drilling many, many small holes. So in theory, I think it's something compatible, but it's not compatible with production cost.
I think that's a really good point, Terry. And I think one of the things you need to talk about is bringing that value proposition to the leadership. You know, is it, if we can drill, say, a 7 7/8 inch diameter hole for trim slots versus, say, 9 7/8, and preserve the wall, get steeper slope angles, reduce waste stripping, what are the economics of that? Similarly with pre-splitting, if we can pre-split that wall and achieve steeper wall angles to reduce the waste stripping, what's the benefit to reducing waste stripping and cost savings there? So I think there's, like, as I said, this should be a lot broader conversation. It should be a lot of economic evaluation that could go into this to facilitate this conversation and determine which way you end up. But to Terry's point, you know, a lot of mines don't want to have the drill steel to drill a 7 7/8 inch or smaller hole to support trims and better distribute energy through a trim pattern. Everybody wants, 9 7/8, 10 5/8. More energy into that hole. Let's move more rock. But again, conversation, engage with all the stakeholders.
It's a common theme in pretty much all topics in mining. All right. Great question, Christian. Appreciate that. Thank you for your answers, everybody. Let's move on to another one. This one is short and sweet. So this is from Chinonso. I observed a case where the blasted slope came out perfectly, but the crest was lost. What could be the reason for this? And I'm assuming blasted slope, I'm assuming we're referring to bench face angle and the crest of that bench. Probably something that a lot of people have experienced.
Was there sub drill in the bench above that could cause the crest to be lost?
Could be, yeah.
100%. Yeah.
Agreed. Look at the cross section from the bench above. That if blast face angle came out perfectly, the crest is lost. That's very likely the root cause.
Or even just maybe you're not holding sub drill, but you're great. Where the drill or the hole's being drilled deeper than it should be. Maybe there was a low spot, and so
energy is directed back directly into the wall, causing crest loss. But in this case, I wouldn't say that slope came out perfectly.
I was talking recently to Eben Robinson of Southwest Energy, and he said your sins follow you down as you're blasting. So certainly, if your sub drill is on your crest, that could be an example of that. Yeah. So, yeah, probably a lot of potential factors. But thank you for the question. All right, we've got a good one from Albert here. All right. Given the potential variability of geology in a mine site. How useful and effective is it to calibrate models based on real field observations? Is it an exercise worth doing, or do the results vary so much that they never meet reality? Sorry, I'm having a little trouble translating. Vary so much that never meet reality or results from future blasts. So is it worth it to calibrate these models based on field observations, or is there just too much variability? If I'm understanding the question.
I will say we have to do it. Today, the technology offer a lot of capabilities to measure in real time the data on the field. I'm talking basically of the seismograph and the measurement right drilling on the smart drills. And this is giving a great information that you can use to calibrate the model. Also, flying the drone before and after the blast to get the terrain before and the mud pile shape afterwards. And using all this data, we have the experience that the model, the digital twin model that we use, you can get to an accuracy that is less than 10% globally. But you have to do it. When I say in real time, it's saying blast per blast. It's not doing it on the 1st of January and expecting it's going to work for the rest of the year. Each blast has to be a new source of data for calibration, and it's an ongoing process. But if you manage to do that, to capture this data every day for each blast, you will see the benefits on calibrating the model and the simulation, definitively.
Yeah, I will add also about this particular point. Sometimes we get lost in the forest, right? Trying to recreate in the computer what exactly is happening on the field. Now, all these models, what will help you is to understand trends, kind of what happens if I increase the frequency of my blast? What is going to happen in the slope? What happens if I increase the PPV and change the timing? Things like that. It's not exactly to reproduce what is going to happen, but at least to see the what if. Is these models, once calibrated, will help you to understand better what is going on the slope. Is what I think.
I think I'd approach this a bit differently and just step away from the phrase calibrate models and not equate that with a numerical model. If you're following the blast master plan process, which I strongly advocate everyone does, that you should be doing this anyway, and you're calibrating albeit a paper model, if you will, on a bench-by-bench basis, and you're making real-time changes on that next bench by observing what happened on the bench above. And so, yeah, it's worth doing, and you should be doing it. Otherwise, to Terry's point, if you only do it once a year, you can't, on January 1, if that's when you start, you can't expect the same results in December.
Yeah, great points. I guess just to follow up, something I'm curious about, is there any stochastic modeling or sensitivity analysis that's done with these types of models? Or is stochastic modeling even feasible?
What do you mean exactly, James?
Stochastic modeling to handle geologic variability.
Okay.
Yeah.
No idea on that.
Yeah.
Sorry.
It sounds like it's not a popular thing if it is done.
No.
Yeah. Yeah. All right. Thank you for the question, Albert. Okay, let's move on here. Got one more question here. Okay. What are your go-to most important considerations you advise to sites when they are working to optimize blasting of slopes? Is there a theme that is persistent from site to site, something you see that is often is overlooked or under-designed? All right, thank you for the question. Really good one. I'm curious to hear Chris's answer to this.
Yeah, the go-to, so high level stuff. The signature hole methodology is very well understood, easily adopted, really. So that absolutely would be a go-to consideration. Make sure you're using the signature hole methodology to optimize the timing configuration for whatever the goal may be. Again, be it the frequency manipulation, amplitude reduction. Again, the goal of the blast given the area that you're in. And then from just a very high level, the energy triangle, the distribution of your explosives, the confinement, the energy levels, understanding cross-sectionally as we approach these slopes, we know that we need to reduce the energy levels and really need to understand that we still have, say, good distribution, if you will, via air decks or physical decks, multiple charges up a blast hole, for instance, depending on the application, the rock hardness, etc. So from again, those would be my go-tos: signature hole methodology and good energy distribution and levels as you approach slopes. I guess further continuing on and turn it over to someone else. The things that are overlooked, under design. The overlooked piece is that I see it a lot where there isn't enough care taken with respect to reducing energy levels as we approach the slope. Not as John said earlier, can't see the forest through the trees kind of deal. That would be one. Yeah, I'd leave it there.
One of the things that I've been noticing is that's kind of under designed is in the corners. Some places it seems like the pattern, they'll start laying out the holes and they won't adjust. Let's say the holes are laid out in a north-south pattern, and then if the corner, as the azimuth changes, they may or may not really be adjusting the production holes to match that azimuth, and you end up in the corners of having excessive burden between your holes. And so again, you can see from the seismograph, the blast is going good, and then all of a sudden it gets to the corner where because they didn't add an extra hole in that corner, or add an extra hole in the corner and kind of space that little bit of extra burden out, distribute it. So you can, if you add one extra, so let's say you're a 20 by 20 pattern, you get to the corner and you need to add one extra hole to kind of keep the same burden, but it drops it down to 14. And so instead of having 20 and then a hole in there at 14, what you could do is you could take that 6 feet of difference and make the 5 holes coming into that corner at 19 by 20 instead of 20 by 20 or whatever your pattern is. And that's where I've seen a lot of our issues. The next issue is when you get in these really tight benches, they're doing really good practice of having trim and buffer and free facing the trim. And then all of a sudden they'll get down to in the corner of the wall, and those practices go away, and there's not enough width to do a trim or a buffer. And so they just load a full decked powder column right up against the wall. And it was all this good work. It undid with one blast. So to me, it's when you do have to do that modified production blast that you're not just throwing away everything you were doing, that you keep, okay, I can't do a separate trim blast here, but I'm at least going to deck the holes. I'm going to do some of those. I'm going to pay attention to my direction of recoil.
Yeah. From my side, I'm fully agree with what Chris and Paul said. And I will just emphasize on the fact that before looking at signature hole and of course energy distribution, come back to the basic and don't forget your free face. Have a clean free face. Allow the movement of the rock on the other side from the wall. And do not direct the waves directly to the wall. Try to use a sequence that direct the waves on the side or perpendicular to the wall. And check your charge per delay for the press split and the buffer. This is the basic things that we have to look at, and we don't have to forget that. And then we can move to the high level technique like the signature holes and things like that.
All right, very good. Thank you all. Sounds like there's a very there should be a little short checklist for everybody. These basic things before they get into the really high level stuff. All right, great question. All right, we got one more here from Christian. How does blast timing optimization have to change in an open pit mine for mitigating slope damage according to faults and discontinuities, apart from pre-splitting and buffers? Thank you for the question, Christian. Really important one. So how do we account for discontinuities? Yep.
Directional shooting.
Directional shooting. Okay.
and a lot of times those are good places to have your stop lines at, because usually one side or the other, there's a different timing domain.
Mm-hmm. All right. Easy answer. You're welcome, Christian. It's a great question. All right. You know what? With that, I think we're out of questions. So we'll give you a little bit of your day back. Before we wrap it up, just like a quick plug for our professional development course series. You can see all of our courses here. Quite a few. You can scan the QR code at the bottom to learn more about the program. And just a quick note that our Fundamentals of Open Pit Slope Design course now has Spanish captions. We are working to get Spanish captions on all of our courses. It's time consuming, as you might know, because of the nomenclature that we can't just put it into an AI chatbot or something like that. It really takes some time. But we got some really great students that are bilingual helping us out with that. So that one is complete. Our next course upcoming this next year will be Geotechnical Fundamentals for Underground Fundamentals for Underground Mining. So if you'd like to learn more about that and register, you can scan the QR code there. All right, with that, thank you to all of our panelists and everybody that participated today. It was a great conversation. I learned a lot for sure. So yeah, thank you all for your time and expertise. Really appreciate it.
Thanks, everybody.
Thank you.
Bye-bye.
All right.
Thanks.
Take care and have a great holiday.